short one. Okay, long and short. Now, so this is I told you before, right? So there's a generator here, generate a DC, rectifier DC to supply to the this seat ring here and energize the rotor. Okay, this is the seat ring. I showed you before this one. Let me show you again. Okay, I will skip this one. Okay, this is a formula. Okay, N to the 120 FOP. Now, one thing I need you to pay attention a bit. Okay, pay attention. The F is the electrical frequency. Okay, what is the mechanical frequency of the rotor? Remember what is omega? What F, right? What's the formula for omega?
2πf.
What's the F?
Frequency.
What frequency?
Hertz.
Electrical, mechanical.
Mechanical.
Mechanical. No, if I ask you in exam or common test, give me the rotor angular speed of the motor or generator, right? This one, right? Rotor angular speed, right, is omega, right? But the F here is not this F, because this F is the electrical frequency.
Right.
So you from this formula, right, from this 1.1 here, right, you find what is the N. This one is what is the formula for N? What is the RPM? Revolution per minute, right? How do you find revolution per second? Yeah? Yeah, by 60 here, right?
Yes.
So this is the hertz, right? So 2 pi N over 60 is the angular speed of the rotor. You follow? Not 2 pi F, 2 pi N over 60.
What's N?
Do you follow?
Yes.
Yeah.
This one, I don't ask you, I don't ask you that. But just now, he tell you, just now you can see, right? The generator need to maintain the frequency and the wattage, right? As a generator, I want to supply you 415, 650 Hertz. You need to maintain the frequency and the wattage. Otherwise, you cause havoc to your system, right? Okay? So how does he control the voltage? Okay? This one is called EA, excitation voltage. The main thing is the voltage generated by the generator and its terminal. EA. Why A? Actually, it's because I consider phase A, phase B, phase C can be EA, EB, and EC.
Don't come with common test.
Yes.
Will they give you the formula?
But this one I won't ask you.
Oh, yes.
It's okay. But this one I won't ask you. I won't ask you this one.
Oh, is that come with common test?
No.
So the exam?
Huh?
Exam come on.
Oh,
Any side.
no, I don't tell you. You need to know. In order to maintain the terminal voltage of the generator, right?
For both examiners.
He can turn
For
faster,
both examiners.
or he can give him more flux per pole. That means he give him more excitation current. That means he need to increase the field current to maintain the voltage. Okay? Okay, I skip this one, okay? Now, this is the one you need to know, understand, because by understanding the structure, right, you can answer the question. Now, this one, the rectangle here is a stator, and the long one here is a rotor. So this is a seat ring. Connect using the DC and supply a current to the seat ring here, supply, energize the rotor. Okay? And this stator, right, have a phase A, phase B, phase C alternating waveform. Okay? Now, look carefully here. A, B, C, right, is the terminal of the generator. Actually, whether it's a motor, induction motor or single machine, right, they have a three terminal, A, B, C, like this. But when you open out the box, actually inside got another terminal. A dash, B dash, C dash. That means it give you 6 terminal. A dash, B dash, C dash. So you see here, with this thing, right, you can connect the winding here become a star delta.
Star.
This is a star, right? How to get delta? Put in the ring. That means A dash to B dash, B dash to C dash. Become okay? Here can be a star, or can be a star, or can be a delta. Up to you. It can up to you to change. But remember carefully, in your exam or in your common test, you have to assume I give you a star. Because it's easier to solve than a delta. I repeat, in your exam or common test, you assume the stator winding are in star. Okay? Now, this is the rotor. I supply him IF, magnetic, is the DC current, right? To magnetize the rotor here, to become electromagnet. So this one is this one here, rotor. And this one, the other one is the stator here. Any question? So I convert for you the physical connection to electrical connection. This is your examination model. You need to know. I will use this model for your exam question or content question. Okay, by the way, I will tell you no such question appear in your exam, only common test. I already changed, I already set up question here. This one only appear in your common test, not exam. Huh? This chapter here, right? Most of the thing, calculation, only appear in your common test. I repeat, only the calculation appear in common test, not in exam.
Then the theory appear in common test, right?
Concept appear in your exam. Concept only.
So common test don't have the concept,
Common test has some concept and calculation. Okay, any question? Okay, yeah, answer your question. Okay?
You got us.
You can see from here, just now, right? I can be a star, right? Or can be a delta. Okay? A dash, B dash, C dash, a stator. Okay? Put a star in your notes. I will ask you this configuration only in your exam. You assume this is the configuration, not this one. Otherwise, you cannot solve easily. Can? In your AC circuit or your ER tech, right? Or in your E-cam, right? You learn 3-phase, right? But for synchronous model, it's very hard to easy to solve. Engineer, right? They try only solve 1 phase. Electrical engineer are very lazy or very smart. They only solve 1 phase. They assume the 3-phase balance. So he only use 1 phase. So for example, E is the EF, right? Actually, EF can be EA, EB, EC. Okay, I show you the other one here. This one here. Okay. Actually, consider this a star point. Okay. Now, look at it here first. This one, right? Assuming there's a neutral here, neutral here. So we are solving this circuit here. A phase to neutral. We assume B to neutral and C to neutral are all the same. You need solve 1 phase. Okay? When the rotor rotates, right? And there's a magnetic field here, right? There's a generate a voltage across here. This voltage will appear here, EA. This is called terminal voltage. This is the voltage supplied to the load. Okay, phase. Okay. So the thing is because to model it, right? Actually the cable itself, the coil itself is very long, yet resistant because it's a coil, inducted. That's why the engineer remodels the equation like this. So there is this one is produced by the generator. Because when the generator rotate and magnetic field, right, it produces a excitation voltage. Here is called excitation voltage. That means that this is caused by the excitation, magnetic field and the movement. This voltage, right, will drop across the inductor and the resistor before appear to the load. Okay, I repeat again. I think you have to assume in your exam, right, this equivalent circuit for one phase. This is the circuit we use. That means when you analyze a single generator, right, for 3 phase, right, you take one phase, and the neutral and the EA or EB or EC, whatever one you need. And then we assume, right, this generator voltage, right, put in series with the inductor and resistor. Okay? And this thing, right, is called synchronous impedance. This whole thing here. Okay? Normally, right, the resistor is very small because the cable they use is very thick. It's a thick cable. Thick cable, right, have very low resistance. That's why it's very small. Then even smaller. For big machine, even smaller because big machine efficiency can be up to 95% or 90%. Very high efficiency. Okay? But this is you have a very high inductor because a lot of coil. So inductor is very high. Do you follow? Now second question I'll tell you, you have to observe this. Smart student, when you solve the answer, you realize something wrong or what. Let's say this is connected to 230. One phase 230, right? What's the voltage here? Higher or lower? Higher, right? Why? Because in order for the power transfer from here to here, right? This is a current direction, right? This one must be high voltage, right? Because the current only flow when the voltage here is higher than this one, correct or not? So in your exam, when you got your answer, your voltage is very small compared to here, right? Something wrong in your calculation. Do you follow? Follow, huh? This one must be higher than him. But as a generator, as a motor, right, this one is higher than the EF or EA. Okay? Okay. Right in your notes, we do not use this equivalent circuit. We only use this one. We only use this equivalent circuit to solve for this one. Okay? Okay?
EF bigger than VT when you is motor.
EF bigger than VT as a generator. Yes. Because current flow this way. For motor, right, current go the other way around. So for motor, VT higher than EF. Okay? We can half an hour late.